Hello class, welcome to today's lesson in which we're going to start the stage number 3, which is about gravitation, power, and energy. So let's get started. So the first thing that we should see is the 3 laws of Kepler of the planetary motion. But I'm not going to explain those to you. I want you to do a little homework on this, and I'm going to explain what this homework is going to be about in a moment. So this is the first thing that we're going to study in regards to gravitation and planetary motion. The thing that I will explain though is the law of universal gravitation. What is this? Well, we know, guys, that in 1687 Isaac Newton, let me write this, wait. Okay, in 1687 Isaac Newton, probably the most popular scientist in the world throughout history, proposed the idea that any two particles attract each other due to their masses, due to their having masses. Okay, this idea is known as the law of universal gravitation and is written mathematically as follows. This is the law of gravitation. This is the law of universal gravitation. Let me explain this to you, all of these symbols. But let me first explain the concept, because that's the first thing you need to understand very well. So Newton, guys, basically what he did was this. He was studying the problem of why objects fall, like if this is the Earth, why objects fall towards the Earth, okay? He was analyzing that problem. He was analyzing the problem of why the moon seems to go around the Earth and all these things. And after a lot of mathematical study and a lot of reasoning, and I mean a lot, he came to the conclusion that any two particles, they don't have to be planets or satellites or anything like that. He went general. He said any two particles, which I'm going to represent by these two little points. Any two particles. I'm going to call this particle 1. I'm going to call this particle 2. These two objects can be anything. They can be planets. They can be people. This one can be a book. And this one can be an apple. This one can be a car. And this can be a house. It doesn't matter, as long as you can treat them as particles. Well, he said, there is an attraction between any pair of particles, like in this case, particle 1, particle 2, they attract one another. And that attraction is obviously in the following way. The particle 1 attracts particle 2. So basically, what that means is that the particle 1 is applying a force on this particle 2. And I'm going to represent that in this way, with this arrow. Okay, this arrow is the force of attraction that the particle 1 applies on the particle 2. Okay, fine. Now, at the same time, the particle 2 attracts the particle 1 towards itself, right? In the opposite direction. This represents the force of attraction that the particle 2 applies on the particle 1. So basically, that's the whole concept. The law of universal gravitation says that any two particles, any pair of particles, attract one another. That's basically the whole idea. Now, how can we quantify that force? It's quantified in this way. Fg is usually written in order to say the force of gravitation. In this case, the force of gravitation between these two particles. And that's going to be equal to the following fraction. G times m1 times m2 over r squared. What is all of these? What are all of these numbers? Well, G, let's start with G. G, guys, is just a constant. I'm going to write down the value of this constant. It's 6.67 times 10 to the minus 11, and that is newtons meter squared over kilogram squared. Now, don't get anxious about this value. It's just a constant, just like pi is a constant, right? Like 3.14, 16, no, 3.14, 15, and many more numbers, right? So that's a constant. The mass of the I'm sorry, the charge of the electron is another constant, okay, etc. So these are constants of nature, and for the moment, just take it for granted. Just accept the fact that that value is equal to this much. I'm not gonna tell you how this is obtained because it's actually quite complicated at this level of high school. So it's just a number. G is just a number called the constant of gravitation, and it's equal to this 6.67 times 10 to the minus 11, and these are the units: newtons times meters squared over kilograms squared. You don't need to understand anything about this other than the fact that it is this value. That's it. Okay, now what is M1 and M2? Perhaps you're already guessing that M1 and M2 are the masses of these two particles. Let me draw them a little bigger. This is the mass 1, this is the mass 2. So mass 1, mass 2. See, that's what M1 and M2 represents. Now, which particle you call mass 1 is completely irrelevant. It doesn't make any difference. And now, what is R? R is the following. Let me erase for a moment these two arrows representing the force of gravitation. And in order to explain to you what R means, R is the distance of separation between the particles, guys. Okay, this distance of separation is usually represented with an R in the context of the law of universal gravitation. Okay, so once again, R is just the distance of separation between the particles. You might think, well, why didn't they just write a D instead of an R, a D for distance? And I don't have a good answer for that. It's just R, and it's been known as R for so many years, so there is no real purpose to having this variable changed. So R means the distance of separation between the two particles. Okay, and that's how you can get the force of gravitation between any two particles, guys. You basically will do just this. You're going to multiply the constant of gravitation, G or big G, we call it usually big G, which is this much, and then you're going to multiply the masses of the two particles, and you're going to divide all of that by the distance of separation raised to the square. And that's how you can find the force of gravitation or the force of attraction between these two particles. It's that simple. Now, legend says, guys, that Newton discovered this law when he was working at home, like for a very long period of time, due to the fact that there was in fact a plague. Like, you can imagine Newton working here completely isolated due to the fact that there was a bubonic plague in England, which so pretty much it's the same conditions that are happening right now in the world. Like, all the people were at home, very afraid of contracting diseases and dying and all these things. And he was working here for a very long period of time, and he actually developed the theory of gravitation and some other aspects of mathematics, working alone at home. Some historians say that this was one of those periods in human history which changed everything. This period of years when this plague occurred in England. So that's just a historic comment. Okay, let's move on, guys. Let me erase this. So, you may be thinking the following. Like, if any two particles attract one another, why don't I see, for example, that if I have my desk, like I suppose you have right now, you have a desk, right? And I don't know, you may have a notebook right there, and you may have a pencil, something like that, or any other object next to the notebook. You may be thinking the following. If I'm telling you that any two particles attract one another, why don't we observe that the notebook and the pencil attract one another? so that they eventually, collide or stick together. Why doesn't that happen? Okay, the reason we don't see that effect, guys, of the two particles approaching one another is due to the fact that there is friction between the notebook, between the surface of the notebook and the desk. Right at this point, there is friction, guys. And the same with the pencil. Between the surface of the pencil in contact with the desk and the surface of the desk, there is friction, okay? And this force of friction is the one that, let's say, uh, keeps them in their place. Even though they are attracting one another, that is perfectly correct. The force of friction keeps them from attracting one another and coming into contact. That is the reason. And also, we should notice that the force of gravitation between very light particles, like a notebook and a pencil. A notebook is about what? I mean, 200 grams maybe, and a pencil is about, I don't know, 20 grams maybe. These are very small masses, and the force of gravitation, guys, is very small for masses like this. In order for you to feel really the power of the force of gravitation, you should have very, very great masses, like the masses of planets and the masses of stars like the sun. It's at these points when the force of gravitation really has some, let's say, some really power. Between particles that are very light, it's not that evident. That's the word. It's not very evident, but it does exist. And if you want me to prove it to you, I'm going to show you a very famous experiment known as the Cavendish Experiment, due to the scientist that made it first. And this experiment is as follows. So look at this, guys. In order to observe the law of gravitation, or the force of gravitation, the force of attraction between two particles that are light, or whose masses are very small, we should be very careful, and we have to make an experimental setup that allows me to see such a small force of attraction. So I'm going to explain to you what's happening here. In here we have the following. We have a metal bar, that is suspended by thread, hilo, in this way. This is a piece of thread hanging from, let's say, the ceiling or something like that. So you have a piece of thread, and then other two pieces of thread. We have a bar, okay, and then we have these four pegs, vertical pegs, these little bars in here. Okay, so what's going to happen? Since this bar is hanging in this setup, in this experimental setup, any small force that you apply on the bar, like let's say over here or over here, is gonna make the bar rotate. Okay, you're gonna observe what it means in a moment. So let's see what's gonna happen. I'm gonna play the video, and I'm gonna explain to you what is happening. So I already explained to you all the setup.
On each.
Now what the person is doing is he's putting two masses at the extremes of the bar. These are metal balls, okay? And as you can see, the bar is like any small force applied on the bar makes it move. Can you see how it moves? With the slightest force, it moves. Now, what's going to happen next? We're going to put two other balls on the other vertical pegs, bars, in here. One here and another here. Now, let me tell you what's going to happen, guys. This is what's going to happen. Okay, so what does the law of universal gravitation says? It says between any two particles, for example, this particle and this particle, there is a force of attraction. This ball will attract this little ball towards itself, okay? And this little ball will attract this ball towards itself. You see, in these directions, and these forces should be the same due to the third law of Newton, Okay, and the same for these two. This ball will attract this ball in that direction, and this ball will attract this ball in this direction, and therefore they should come together. Now, given the experiment, given the way the experiment is set up, we can actually observe the force of attraction between these small balls and the big balls in the following way. Let's take a look. Can you see how they are approaching one another? And the bar is rotating due to that force of attraction. Can you see? Now, why are the big balls at place? Why don't they seem to be moving towards the small balls? Because they are fixed. If you notice in here, they are fixed to the metal, to these little bars. Let me show you that again. That's the force of attraction at play, guys. You're witnessing a confirmation of the law of universal attraction for small masses. But in order to observe this, I repeat, you have to have a very, very careful experimental setup. Otherwise, this is pretty much impossible to observe in everyday life. But it does exist. It does exist. Nice. Okay, so let's go through 3 examples, guys. Let me show you. Let me see how much time it's been. Okay, 60 minutes. Maybe I can show you 1 or 2 examples, and then we can do another one in class. Okay, so these are examples of the usage of the law of universal gravitation, which I repeat is this. You don't have to memorize it. It's going to be appear in the exams and so on. Just understand what each of these symbols mean. So let's start. I'm going to use my calculator in a moment, so I have it by my hand, and let's do it. The example 1 asks me this. Calculate the force of gravitation between 2 people which are 1 meter away from each other, okay, and their masses are 70 kilograms and 60 kilograms respectively. Okay, so let me represent the people by 2 point masses, 2 particles. Person 1, person 2. The mass 1 of the person 1 is going to be 70 kilograms. I could have used also 60. It doesn't make any difference which one I call the mass 1. It doesn't make any difference at all. And the mass 2 for the particle 2 is going to be the other one, right? 60 kilograms. Okay. Now, what is the distance of separation? 1 meter. Because they tell me that these people are 1 meter away from each other. So I'm going to do that in blue. The distance of separation between these 2 people, which is usually represented by an R, like I told you, is 1 meter. There you go. And now we have all the ingredients to calculate the force of gravitation between these 2 masses. Why? Because I have the masses, I have the distance of separation, and I know that the constant of gravitation, big G, is equal to 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared. This constant will also be given to you always in the exams, in the problems, etc. So you don't need to memorize this. Okay, so what else do we need? We need the law of gravitation that says that the force of gravitation between 2 particles is equal to the constant of gravitation, G, times the multiplication of their masses over the distance of separation, R, to the square. And basically, guys, all we need to do is substitute the information that I have discovered in this part of the problem in my formula. So let's see. The force of gravitation will be equal to G, big G, which is this number. So let's just write it down. There you go. And then the mass 1, which is 70 kilograms. And then the mass 2, which is 60 kilograms. divided over the distance of separation, r to the square. So 1 meter to the square. Okay, and that's it, guys. All we need to do next is just perform this arithmetic, this value times this value times this value over 1 to the square, and I'm done. Now for that you will always use a calculator, right? Because those are very complicated. Well, not that complicated, but they may be a little tricky to do by hand. So what I get is the following. After I perform all of this stuff, I get the following result. 2.8014 times 10 to the minus 7 newtons. Why newtons? Because we're talking about a force, and force is measured in newtons, as I told you before. So this is the answer, guys. And as you can see, the force of gravitation between two people that are just 1 meter away from one another, like they may be talking, they may be chatting 1 meter away from one another, this is the force of gravitation that there is between these two people. 2.8 times 10 to the minus 7 newtons. That is a very small force. A very small force. If you wrote this in standard notation, that would be that the force of gravitation is equal to 0.00000028014 newtons. It's this small. Obviously, this is written in scientific notation, which is the notation that you should use as much as possible. But if you transform this into standard notation, this is how it looks. Okay, it's really, really small. That's why you don't feel it. When you're in front of somebody talking, guys, you don't feel any force being applied on you by the person, right? Because it's just very tiny. It's extremely, extremely tiny. That's the reason. Nevertheless, there is a force. Okay, be aware of that. There's a force between these two people. Okay, example number 2. Calculate the force of gravitation between the Earth and the Moon. Their masses and the distance of separation r between their centers are given below. So let's see. Now in this problem we have the Earth and the Moon. So let me draw them. Earth and Moon. Okay, these are the centers. This is the center of the Earth. This is the center of the Moon. And I know the mass of the Earth, which is this much. I was given this value for this problem. The mass of the Earth is this many kilograms. It's a lot, obviously. And the mass of the Moon is this many kilograms, which is also a lot. R, which is the distance of separation, is this much. But be aware, guys, that when you consider objects that have volume, like a very large volume, like planets or stars, stuff like that, the distance of separation that you should consider is not this distance, the distance between their surfaces, because this is a distance perfectly valid, but this is not r. R never means the distance of separation between the surfaces of the objects. What r means is always the distance of separation between the centers of the particles that you're studying. So this is the center of the Earth, this is the center of the Moon, and in this case r, which is this value, is the distance between here and here. That's what r means in this case, and it's this much given in kilometers, and we're gonna have to convert that into meters in a moment. And g, as always, is this much. Okay, so we have all the ingredients to calculate the force of gravitation between the Earth and the Moon. So the force of gravitation, according to the law of gravitation, is equal to g, big G, times mass 1 times mass 2 over the distance of separation to the square. And all I need to do next is fill in these variables. So g, I just write down the value for big G, which is this much. Just write it down like that. And for the mass 1, which is the mass of, let's say it's the mass of the Earth, so I'm gonna write this number, 5.97 times 10 to the 24 kilograms. And the mass 2 will be the mass of the Moon in this case, 7.34 times 10 to the 22 kilograms, over the distance of separation between the centers to the square, which I was given and is equal to this many kilometers, 384,400 kilometers. Okay, pay attention to what I'm gonna say, guys. These units, the units in these problems, should always be official units. Official units. Okay, what I mean by official, the units in the international system. The unit for length in the international system is not the kilometer, it's the meter. That is the official unit. So if you're given the distance of separation in kilometers, you need to transform this into meters before you substitute in the formula. Now, how many meters is this? Well, it's gonna be, and just multiply this by 1,000, right? Because a kilometer is 1,000 meters. So it's gonna be this many meters. That's it. This value and this value are the same, but this is written in official SI units. So that's the value I'm gonna put in here. If I don't do that, guys, I'm gonna get wrong results. And this is elevated to the square, like you can see here. Okay, now all I have to do next is the arithmetic. Multiply this quantity times this quantity times this quantity and divide that over this quantity to the square. If you want, oh, by the way, I forgot something here. I forgot the units, right? Meters to the square. Okay, and at this moment, if you want, you can ignore the units, like this and this and this and this. Just ignore that. Just multiply the quantities, the numerical quantities. And well, let's stop the class right here. Give me this number. In a moment, I'm gonna ask you for the whole simplification of this, and you're gonna give me that number, newtons, which is gonna be the answer to this problem. And the example number 3, we're gonna do it together. I wanna stop the lesson right now. So please calculate all of these, guys, this expression, and I'm gonna ask you for this number in a minute or two. So let's do it, guys.